And I'm recording and I have audio. All right, last time we were doing conversions. And we looked at converting 5,000 feet into meters. And it came out to, I don't know what, 1,500, 1,600, something like that. Point is, we looked at it and we treated it like it was a measurement of 5,000 feet with one significant digit, which meant that when we were finished with all our calculations, our final calculation was 2,000 feet, 2,000 meters, one significant digit. But if that 5,000 feet were not a measurement, if we were just asking how many meters are in 5,000 feet, then we would have treated it like a defined number, well, not a measurement. And our answer would have been the original that we came up with, the 1,624 or whatever it worked out to be. I don't remember the number, but this is the important point that I want to make sure you pick up on, is that numbers that are defined have infinite precision. When you make the transition from feet to meters with 2.54 centimeters per inch, that's 2.54 plus however many zeros you need. It is considered infinite precision. So don't use any of these defined conversion units, these defined quantities like this, do not count when you start looking at significant digits. The only thing that matters when you look at significant digits are the measured values. If something was measured, then you have to consider the precision of the measurement as well as the accuracy. Now, who can tell me the difference between precision and accuracy? Yeah. And do you think there might be a reason I keep asking y'all about that one? Because this is what, the third time? You think maybe it might be because there's some cheap and easy free points on the next exam that's coming up that you might be able to snatch up if you know the answer to this? Somebody hold up their hand and tell me what's the difference between precision. Go ahead. Accuracy is how close the measurement is to the actual value. What is precision? Exactly. Precision is the resolution of the measurement. How many decimal places are in the measurement? If we measure this room, the length of this room, I'm coming back to this same example because it's hyperbolic, but it makes the point. I can measure this room and I measure it to 24.87 inches in length. Then the precision of my measurement is 24.87, and black, I remember. 24.87 inches. That's inches, that's tenths of inches, that's hundredths of inches. So the precision of that measurement is down to the hundredth of an inch. Implicitly, it would be plus or minus 5/1000ths of an inch if we were talking about the precision. But what about the accuracy? How accurate is this measurement if I measure the length of this room to 24.87 inches? So not a rhetorical question. Someone say it out loud. How close is the width of this room to 24 inches? Not very close at all. That's a very inaccurate measurement. Don't care how precise the instrument is, how many decimal places of resolution it can give me is irrelevant if it's that inaccurate. So, everybody wrap your mind around the difference here. And yes, I'm giving you a big signal about some easy points on this exam if you know this and remember it. Now, we're going to talk about converting units. And before we do, I want to go back and cover some things with you about exponents, because we use exponential notation when we talk about units, when we write units. So this is just revisiting some mathematics. We know that x cubed means x times x times x 3 times, right? X to the 5th would be x times x times x times x times x 5 times. Deja. What if we multiply x cubed times x5? That would equal x times x times x, x cubed, times x to the 5th. All right? That should be this, and yes, this should be very boring to you. It should be very obvious, but I'm taking it one step at a time because I think you're going to get something out of this when I get to the end. What we have here is 1, 2, 3, 4, 5, 6, 7, 8. So that would be x to the power of 8, which is actually just equal to x to the 3 plus 5. So when you're multiplying factors with exponents, you add the exponents. What about if we divide? X to the 5th divided by x cubed. That would be 1, 2, 3, 4, 5 divided by 1, 2, 3. Well, these cancel, and these cancel. They cancel because x divided by x is equal to 1. This x divided by x is equal to 1. So this is basically saying x times 1 times 1 times 1, which is x, which leaves x squared. Well, notice that x squared is equal to x to the 5 minus 3. So when you're dividing with exponents, you subtract the denominator from the numerator. What happens if we divided x3 by x5? X, what's 3 minus 5? Negative 2. That's where we get the negative exponential notation from. Now, what if, I've told you before, division is just multiplication by a reciprocal. Well, what if we did that? What if we multiplied by 1 over x squared? We have x3 times x to the minus 2. What does that give you? 3 minus 2 equals x to the 1. Now, I told you yesterday, or Monday, that anytime something is raised to the power of 0, anything raised to the exponent of 0 is equal to what? Equals to 1. Do you see how that falls out of the way these exponents, we're treating these exponents? What if you have x to the 4th divided by x to the 4th? That's anything divided by itself is equal to 1. But that's also equal to x to the 4th times x to the minus 4. And when you add the exponents together, what do you get? X to the power of 0. That's where this comes from. Now, there's one more definition I told you about exponents, and that is if you have an exponent that is a reciprocal. Everybody remember what a reciprocal is? The reciprocal of x is 1 over x. By definition, reciprocal is whatever number you have to multiply a number by to get 1. So, what if we were writing the square root of x squared? What does that equal to? That's equal to x, right? And it's equal to x squared times some other exponent. And that is equal to x to the power of 1. So what exponent will you multiply 2 by to get 1? R would then be 1/2. So, again, this is where these definitions come from. That's why if you want to write x, the square root of x, you write x to the power of 1/2. If you want the cube root of x, it would be x to the 1/3. Or the nth root of x is x to the 1 over n. Now, I don't know, maybe this is boring to y'all, or maybe this is old news to y'all, but this was something that always kind of puzzled me when I was first learning all this material back in undergraduate school. So, thought it might help you. Now, anybody have any questions so far? Oh, Megan? Where'd she? There you went. There you go. When I write units anyway, we write units the same way. You can either write, if we're talking about speed, we write distance, meters per second, or meters divided by seconds. That means I can also write that as meters times seconds to the negative 1. What happens when we multiply speed? What's the quintessential word problem? How long does it take? How far does a train going 80 miles an hour go if it drives for 1 hour? Well, it goes 80 miles. How do we get that? Rate times time equals distance, right? So if we've got meters per second, and we multiply that quantity by seconds, we've got meters to the power of 1 times seconds to the negative 1 times seconds to the power of 1. What is seconds to the negative 1 times seconds to the 1? That's seconds to the minus 1 plus 1 which is seconds to the power of 0, which is unity. Okay? So, meters per second times seconds, the seconds go away and we're left with meters. Rate times time equals distance. Everybody with me so far? We could also write this meters per second times seconds, where we see the seconds canceling each other out, because seconds, anything divided by itself is unity, 1. Y'all would help me a whole lot if y'all would ask some questions. Or am I really getting that boring? This is all old hat to everyone. So, let's work through example 1-3. It's on page 11 if you're following along in the book. There are only 14 peaks whose summits are over 8,000 meters tall, above sea level. They're the tallest peaks in the world and are referred to as the 8,000ers. Wonder why they got that name. What is the elevation in feet of an elevation of 8,000 meters? All right. First of all, is that a measurement? How many significant digits are we going to be working with? Say again? If this were a measurement, we would only have one significant digit. But we're not asking how tall is this thing that we measured to be 8,000 meters. We're saying 8,000 meters is the quantity. It's the exact quantity. How many feet is that? So we're going to treat it like a defined quantity and just keep all of the digits. So, where do I start? How do I convert meters into feet? These conversion factors would sure be handy things to have on an index card when you're taking an exam. Not that I'm dropping hints or anything, but what conversion factor are we going to use? What definition will get us from meters to feet? Somebody over here. Bingo. Only here's a little notation for everyone. Have you noticed that every once in a while I'll write an equal sign with 3 lines instead of 2? Does everyone understand what that means? It means this isn't just an equation, this is a definition. That means this is as precise as you need it to be. It's 2.54 plus as many zeros as you can use. So an all-you-can-eat buffet. So, if we can get to centimeters, we can get to inches. How would we get to centimeters? Yep, and how would we do that? 1 meter equals 100 centimeters. So we're going to multiply this. We want centimeters left over, which means we want meters at the bottom so that the meters will cancel out. Well, there are 100 centimeters in every 1 meter. So this gets us from meters to centimeters. How do we get from centimeters to inches? Okay. The centimeter is in the numerator, so we're going to want centimeters in the denominator here. That'll leave inches in the numerator. And that would mean, what numbers do I write here? 1 over 2.54, or 1 inch per 2.54 centimeters. And that gets us to our centimeters cancel, and we now have 8,000 meters converted into some number of inches. How do we get from inches to feet? 12 inches equals 1 foot. So what do I write? And the inches cancel, and that gets us 2 feet. So now we take, in our calculators, 8,000 times 100. Divide that by 2.54. It equals something that you then divide again by 12. And that gives us what do you come up with? You, Luke or Logan? Luke. Oh. Who over here's got the answer yet? Don't call out the answer, but does anyone over here have the answer yet? You got it? You got it? You got it? Since we were converting to feet, round it to the nearest foot. Okay, to the nearest foot, that would be? Did you get something different? Deja, did you get something different? Did anyone get anything different? Okay, well, let's repeat this, but this time let's go the other way. It is said that Mount Everest is 32,000 feet tall, correct? If that's not correct, we're still going to pretend like it is. Now, and again, we're going to assume that this is a definition, not a measurement. Although it actually would be an approximation. So we could very easily justify only using two digits, but we're going to pretend like it's an exact number, at least an exact number of feet, and we'll keep everything to the foot. So, somebody help me out. What's the first thing I'm going to do? What do I write next? I'm going to have a ratio of numbers and a ratio of units. Inches on the top, feet on the bottom. What about my numbers? 12 inches equals 1 foot. Okay. Then what do I multiply by? What comes next? Numbers and units. I'm going to have centimeters per inch, which will be 2.54 over 1. Okay? Next. And that means I've got 100 centimeters for every meter, so that's 1 meter per 100 centimeters. That gets us to centimeters cancel, inches cancel, feet cancel. That gets us to meters. To the nearest meter. Over on this side this time. You got it? Everybody else got it? You got it yet? Shy, you got it yet? Anybody over here? Everybody over here got it? What'd you get? 975? Okay, what did you get? Yeah, I think you lost a decimal place somewhere. $9,753. Now she got me doing it. .6. How much is that to the nearest meter? Meters. Is everyone getting to how this was done now? Because you want to, by what you want left over and what you want to cancel out. You put what you want left over on top and what you want to cancel out from before on the bottom. See here you've got feet. And you know you want to cancel the feet and leave with inches left over, so you put inches on top and feet on the bottom. Now, when we get into some of this later on, we'd be talking about, like for example, if we were talking about hertz. Hertz are what? Anybody remember hertz? Or have anybody studied hertz yet? Hertz are defined as cycles per second, or only cycles are unitless. There's no unit associated with cycles. So the actual units for hertz are just 1/seconds. Now, if you were converting hertz into, I don't know, cycles per hour or cycles per day, then you would start off with some number in the inverse seconds. How would you, well, you know what, rather than do this abstractly, let's do this example, because this is it's a good thing to do. Help you get straight how you know what to put on top and what to put on bottom. Let's say we have a signal that oscillates 4 million hertz. So it's 4 times 10 to the power of 6 inverse seconds, or per second. How many oscillations does it go through in 2 hours? Where do we start? Let's start by talking about that. What conversion factors are we going to use? We've used 1 inch is defined as 2.5 centimeters. We've used 100 centimeters. It's defined as 1 meter. What conversion factors are we going to need for this? We're going from seconds to hours. 1 hour defined as 60 seconds. No, it isn't. Somebody's trying to make me look stupid. What is it? 1 hour equals 60 minutes. What else will we need? 1 minute equals 60 seconds. What if we wanted to skip a step and just go directly from seconds to hours? How would we get that conversion factor? Right here. 1 hour equals 60 minutes. What if we wanted to go directly to seconds? Yeah, but why? Go one step at a time. Right, 60 seconds per minute. The minutes cancel, and we're left with 1 hour equals 3,600 seconds. 60 times 60. But let's not skip this step. For the purpose of this exercise, let's go one step at a time. We got 4 million, 4 times 10 to the 6, inverse seconds. What's the first thing I'm going to convert over here? I have a number over a number and a unit over a unit. Seconds to minutes. Which one goes on top? Okay, but which one do I put on top and which one do I put on bottom? Okay, let's do it that way. Now, what I've got here is I'm going to use min instead of m to make sure we don't confuse it with meters. And I've got min times 1 over seconds multiplied by inverse seconds. When I add these inverse seconds to inverse, when I multiply these together, what do I end up with? It would be, this would go to minutes per second squared. You see what's happening? This is going directly to your question from a moment ago. How to know what goes on top and what goes on bottom. Position everything so it will cancel. In this case, we want to cancel out 1 over seconds, which means we need seconds on top and minutes on bottom. Now, seconds cancel out because s to the negative 1 times s to the 1 equals s to the 1 minus 1 equals s to the 0 equals unity. So, we've gotten the minutes. What are we going to next? Number over a number, unit over a unit. Okay, what do I want to cancel? I want to cancel minutes, so where do I put minutes here? On top. That means hour goes on bottom. And I've got 60 minutes per hour. And that means I now have some number per hour. So what's 4 times 10 to the 6 times 60 times 60? Whoever gets it, call it out. $1.44 times 10 to the 10 inverse hours, or however many bajillion, however many, that's what, 14.5 billion per hour. 14.5 billion cycles per hour. Right? Now, we've got rapid estimating here in section 1.7, and we're going to come back and look at it. But I want to, while we're talking about this, I want to go ahead and show y'all on the last section we talk about dimensions and dimensional analysis. First question, what's the difference between dimensions and units? MKS, we have length, we have mass, and we have time. In MKS, length is meters, mass is kilograms, time is seconds. In CGS, length would be centimeters, mass would be grams, time would still be seconds. If we were in SAE, American foot pounds and stuff, length would be feet, or maybe inches, or miles. Mass would be in, thank you, slugs. Time would still be in seconds. All of these are units. These are the dimensions that those units define. Okay? Length, mass, time are dimensions. And whenever the book has you doing dimensional analysis, it's going to show you writing these inside square brackets to call attention to the fact that you're dealing with dimensions, not units. So if we were going to do a dimensional analysis of rate times time equals distance, what are the dimensions of the rate, of our speed? Okay, well, the units of speed are, somebody call it out. You can play too. Miles per hour. Those are the units. What are the dimensions? Miles. Miles is length. What is hour? What dimension is hours? Time. So, the dimensional analysis of rate would be length over time inside square brackets. Now, if we were doing rate miles per hour times 14 hours, then we would multiply this by some number of hours, which is what dimension? So this is a dimensional analysis of rate times time. You've got length per time times time. Your times cancel out, and that leaves you with dimensions of length. Okay? We could do this with force, with distance, with power, energy. Point is, you don't work with the units, you work with the dimensions that the units define. And you make sure that everything works out the way it's supposed to. If you're analyzing rate times time equals distance, you write the dimensions of a rate, multiply by a time, and make sure that you're left over with a dimension that of distance or length. Now, let's talk about estimation, rapid estimation, or order of magnitude rapid estimation. Why do we care about this? Because I will tell you honestly, I actually thought about just eliminating this whole estimation thing out of the course altogether. I decided not to for two reasons. There are two reasons that I want you to learn rapid estimation, or just estimating in general. And we've talked about them. So who remembers? What's the first reason you should learn about estimation? Say again? It is a guess, but the question is, why would you want to guess? Why would you want to be able to just, at least to within some modicum of accuracy, be able to at least guess instead of actually measuring something? I mean, I use the example of measuring the length of this room, but the fact is, these are 12-inch tiles. It's not that hard to count them. Why would I try to guess? Oh, I don't know, it's about, what, 20 to 30, say 25 feet long? Well, it's easy to just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Looks like I was off on my guess. 21, 2, 3, 4, 5, 6, 7, 8, 9, 30. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's closer to 40 than 25. Why would I even bother guessing when it's that easy to count? Because sometimes it's not that easy to measure. Sometimes it's just not possible to actually measure. You're talking about what's the volume of a lake? How much water is in a lake? You're gonna go out to the lake with a measuring cup and start scooping and bailing. You're going to be bailing for a long time. You can't physically, it's just not practical to measure the volume of water in a lake. Sometimes you don't really have a choice but to make a best guess, or at least an order of magnitude estimate on how much water is there. And if you think it through, you can usually estimate at least to an order of magnitude or so, give or take. So they use the example of a volume of a lake here. It's an irregular shape. It's not a perfect circle. It's got a curvy shoreline. You're not gonna be able to go out with a surveyor's transit and cartographically map out that whole shoreline. I mean, maybe you could if you've got a year or so to do it, but and it's not a constant depth. I mean, you've ever, I don't know if any of you have ever scuba dived, but if you go down a little, I'm sure you can all envision what it looks like at the bottom of a lake or a pond. It's not like a swimming pool that's got a nice rectangular hole dug in the ground with a flat bottom. You know, so deep over here, so deep over here, a nice slope between them. If it was, well, then you could calculate the volume of water in a pool. But a lake has this irregular bottom it's not going to be the same depth in any two places. But you can measure the average depth with a sonar, or you can estimate the average depth based on extrapolating from the slope of the surrounding hillsides and guessing, okay, well, it's probably about this deep on average. And it's a irregular shape, so you can't tell exactly what the perimeter is, but it's about kind of circular. And so it's approximately some diameter across, and so you approximate it as a circle of some average depth, and that you can count the volume for. It's the area of that circle times that depth gives you some approximation of volume. It's not going to be accurate. Remember that precision versus accuracy? Your estimation is not going to be that accurate, but it's at least going to be in the right ballpark. And so when that's all you can do, that's at least a good place to start. Sometimes you can... How many of you are familiar with iterative processes? What does iteration mean? You've taken calculus. You got to know, right? You don't know iteration? Anybody? Okay, forget math. Think English. What does it mean to iterate? To repeat. Exactly. If you reiterate, you're repeating yourself. Sometimes you don't know a value, but if you can get a good guess, then you can do a calculation based on that guess and find out how closely it agrees with something else. And based on how closely it agrees, you can go back and adjust your estimation and recalculate, and then adjust this estimation and keep recalculating the two, keep changing the estimations back and forth, going through iterations until you come up with some agreement between them. That's one way to address solving some problems. So the ability to do estimations may seem kind of counter to the point of a physics class where the whole point is learning how to measure. You know, that is science, the study of what we can measure. But it is important. Now, there's one other reason I want you to... I decided not to get rid of this whole estimation part of the class. Who remembers the second reason? Sometimes it's the only way you can go forward, just with the best guess you can make. But there's a second reason, and I talked about it. Who remembers it? Sometimes your finger's going to miss that decimal point, and you're going to end up with a number that's off by a whole order of magnitude. Sometimes you'll especially when you start working with scientific notation, you're going to, you can hit the wrong, you forget to put that minus sign on that big exponent in your power of 10 notation, and now you haven't just changed by one order of magnitude. If that exponent was a 10 and you leave off that sign, you've just changed your answer by 20 orders of magnitude. If you can estimate, then you can at least have an idea of what your answer should be. And that's something I want you all to practice to constantly think about as you go through this course. When you're doing a problem, when you're doing calculations, think about at the end, when you get the answer, look at your answer and think, is that a reasonable answer? Okay? I'm looking for the height of Mount Everest. Mount Everest is 32,000 feet. Is it reasonable that my answer is only 900 meters, less than a kilometer? Well, if you know a kilometer is, what, half a mile? And a mile is 5,280 feet. And if Mount Everest is 30,000 feet, then that means it's coming up on 5 miles tall. All of a sudden, less than a kilometer doesn't make a lot of sense. And if you're thinking like that, you'll pick up on these mistakes. And if you're not, if you're just trusting your calculator, you'll end up coming up with some answers that just aren't even close. You know, these are the kinds of mistakes that happen to every single last one of you. Most of you have been fortunate enough that I haven't been calling on you when you made that mistake, but every one of you makes these kinds of mistakes. By thinking in terms of estimations, you can get in the habit of thinking about your responses, your answers you come up with, and know whether or not they're reasonable. Now, the example we give here, we got about 4 minutes, so let's do this example of a rapid estimation. They give the volume of a lake. And they say, well, this lake is approximately 1,000 meters across. And it's approximately 10 meters deep on average. That means the radius of this lake is 500 meters. Approximately. Based on these numbers, then, what would you guess the approximate volume of the lake is? Well, what's the area of a circle? Okay, side point here. Show of hands. Who knows the formula for the area of a circle? Seriously, raise your hand if you know the formula for the area of a circle, or the volume of a sphere, or the surface area of a sphere. I'm just asking this not because it really has anything to do with rapid estimation, but it just seems to me like these are the kinds of things that would be handy to have on an index card if you ever found yourself in a bind and needing to know the. But pi times radius squared is the area of that circle. Area times depth is the volume. So our volume will be approximately equal to pi times 500 meters squared times 10 meters, or approximately 3.14, which we're just approximating, so we're going to drop the 0.14. Okay, 3 is pretty close to pi. 500 squared is what? 2,500, 25,000, 250,000. What's 5 squared is 25. And then you're going to have how many zeros once you've squared it? 4 of them. So it's going to be about 3 times 250,000 times 10, or about 3 times 2.5 million, or about 750 million Meters squared times meters, cubic meters. What if we did a dimensional analysis to make sure we were right? Pi is unitless, so it doesn't reflect a dimension. We're taking length squared and we're multiplying it by a length. And that gives us length cubed, which is volume. So we end up with about, 750 million cubic meters, give or take? What does the book come up with? Or do they even keep the 3 from the pi? No, they end up with 8 times 10 to the 6. Any questions about how this works? Any questions about the homework assignment? All right. Then I will see y'all tomorrow for lab. Did everybody sign the sign-in sheet? Where is the sign-in sheet? Did anybody not sign besides you?